Welcome to fifth in the series of lecture for work, power, energy. A quick recap. So we have looked into this idea of total mechanical energy, which is equal to kinetic energy plus potential energy equal to constant, right? So this is basically your law of conservation of, this is consistent with your law of conservation of energy, which is total energy is constant and energy is neither created nor destroyed. It's changed from one form to another. So the change happens between the kinetic energy and the potential energy, and the sum is always constant. So that's the whole idea. That's how it fits into this law of conservation of energy. And further, we also talked about its idea that potential, it's actually potential for energy and not potential energy. And potential energy is always of a system, right? So let's say, for example, a system could be the earth and the ball system. So here there is a force which is gravity, so and that force helps in the interaction between earth and ball. So in this particular scenario, this we call all this ball, earth, and this gravity as one system. So when we say potential for energy, it's between the ball and the earth system. So it's different. The potential for energy will be different in the moon ball system. There your force that moon exerts on the ball may be very different. So remember, it's of a system. If you remove earth and bring some other planet, it changes. If the ball change, it's some other mass other than the ball, then the potential for energy idea changes for that system. And it's introduced to make law of conservation of energy work. So in the last series we saw how the total energy is constant, which is kinetic energy, and potential energy is constant. So the whole idea of potential for energy is a virtual concept. It was introduced to make the law of conservation of energy work for us in physics. And remember that it can be applied only for certain scenarios and certain types of forces like gravity and spring. So in this lecture, I'm going to delve into a little bit more details of how it applies to gravity and springs. So the first example is, already we have seen this. So if you have a ball that is falling from a height h, which is point A to point B, and if you look at any intermediate point C, so if you look at this, at A you have a very high potential energy which is given by U, and your kinetic energy is 0. So K. So this is your mgh, this is 0. So total mechanical energy mgh. Similarly, at C you have part of the kinetic energy is converted into kinetic energy. We visualize it like that. The potential for energy is converted to kinetic energy, and here again your total mechanical energy is going to be mg into h minus x plus mgx. That's equal to mgh, right? And this is always your x, and this is your h minus x. The net height is h. So finally you have at the final point you have U is 0, and almost all the energy now is converted into your kinetic energy. So this should be a little bit, yeah, it should come down here. So that's your kinetic energy, and that's your kinetic energy, and your potential energy is this. So your TME, your U plus K, that's equal to 0 plus mgh, and that's how it's constant. Now you can extend this whole idea for pendulum. Now a pendulum is an oscillating, we say that's a pendulum follows a simple harmonic motion, or something that's, it swings from one end to another, and as it goes to its both extreme, we have something similar that we have seen in the previous case. At this point, the whole pendulum is lifted by a height h, so it has got maximum potential energy, and your kinetic energy is 0, so there is no velocity at this point for A. And for B, you will find that it does not have any potential energy because the pendulum is at its lowest point, and all the potential for energy here has been converted into your kinetic energy, right? Your K, and this is your U. U is 0, and here it's K. And when you consider this point C, you have a situation where, exactly like A, all the energy is converted back into potential energy, and the pendulum has 0 velocity at that point. So this is your K, and this is your U. And it follows the same principle that your total mechanical energy is U plus K, that's equal to constant. So again, all your potential energy at this point is converted to kinetic energy at this point, and again it goes back and converts to potential energy, and kinetic energy is 0 here, and the whole thing goes to and fro. You can imagine a similar condition, similar state for your for a spring. So let's assume that this is your spring, and this is your spring, and this is your point. This is your mean position of the spring. As you extend the spring towards here, so as you extend the spring towards here, so this is your point A, and you leave it. So as you extend this and leave it, what happens is there is a restoring force, so this A is pulled back, and the graph would be exactly same as for a pendulum here. So all the potential energy is stored in the spring as you stretch the spring, and there's a lot of potential energy we say is stored in the spring. Now remember, this is a virtual concept. This is an idea which we have introduced. Potential for energy. So we say potential for energy is stored in the spring, and initially there is no velocity, so K is 0, and as you leave it, it goes back to the point B, where the velocity is maximum but the spring is not stretched or compressed, so there is no force from the spring but just the inertia due to the velocity. So it's a very high kinetic energy at this point, and then it goes to its point C, where it compresses the spring. And so this is compression, and this is stretch. As it compresses, the body comes to rest, and then there is a force. There is a force in the opposite direction, due to which we say that all the potential energy now is going to, all the kinetic energy is stored as potential energy at C, and so this is your C. This is a graph of that. And due to the restoring force, again the block starts moving, its kinetic energy increases, and then here again kinetic energy gets translated into potential energy and so forth. So the same thing as pendulum. So these are examples of cases where potential energy, the idea of potential energy applies, and you can apply your law of conservation of energy.